In the second part of chapter 4, we're going to be dealing with applications of derivatives. Now, I know the section says 3.4, but it's really, it's 3.4 in our textbook, but it's the second part of chapter 4 in our course. So if we take a look at or recall from section 2.4, the difference between average rate change and instantaneous rate change. Average rate change was the slope of a secant line. So if we had some curve and we had 2 points and we found the slope of that secant line, that would be average rate change. But if we had a tangent line at one particular point, that would be instantaneous rate change. Example 1, we're asked to find the rate of change of the area of a circle with respect to the radius, and they want us to evaluate the rate of change of A when the radius is 5 and the radius is 10. So to start with, we're going to start with the formula for the area of a circle. Area is pi r squared. And we want to take the derivative with respect to the radius. So that means our variable of differentiation is r. So that means dA dr, which is the change in area with respect to the change in radius. If I take the derivative of the right-hand side, would be 2 pi r. So now, to find the change area with respect to radius when the radius is 5, I would just plug 5 in for r. This works out to be 10 pi. Now, as far as units go, the area would be meters squared, and the radius would be meters. Now, that looks kind of odd, but if you think about it, this really means that the area is changing by 10 pi meters squared for every 1 meter increase of the radius. Now, if I wanted to find the change in area when r is 10, it would be 2 pi times 10, which would be 20 pi meters squared per meter. Okay, now we're going to start looking at position, velocity, and acceleration. Instantaneous velocity is the derivative of our position function. And in physics, we use position, which means the same thing as displacement. And quite often we use the variable st for position. So therefore, velocity is the derivative of position with respect to time, or s prime of t. Speed is different than velocity, and speed, because it's a scalar quantity, is the absolute value of the derivative of the position function, because speed is always positive. Acceleration is defined as the derivative of velocity with respect to time. So acceleration is the derivative of velocity, so it really is the second derivative of the position function. Usually when we deal with two types of position functions, horizontal motion, we usually denote our position as s of t. Vertical motion, we denote as h of t. Again, sometimes on the AP Tough exam, they'll use x of t for position, but they'll clearly state that in the problem. Okay, let's take a look at our first example. A ball rolls along the x-axis so that its position in centimeters after t seconds is given by the formula t cubed plus 3t squared. Find an expression for the velocity at any time t. While velocity, whoops, lost my page there. Velocity is equal to the derivative of the position function, so it would simply be 3t squared plus 6t. Part B, we want to find the velocity when t is 5. So again, all I'm going to do is I'm going to plug 5 in for time into the velocity function. So this is going to be 3 times 25 is 75 plus 30. So this would be 105, and my units would be centimeters per second. Now note the difference here, and here they want us to find the average velocity. To find the average velocity, remember that is the slope of the secant line. So that's really the position at time 2 minus the position at time 1 over time 2 minus time 1. And if you think about it, position is measured in meters, or centimeters in this particular case. Time is in seconds, so my answer would be centimeters per second. So to figure out average velocity, it's going to be the position function at time 5. So my position function was t cubed plus 3t squared. So it's going to be 5 cubed plus 3 times 5 squared minus the position at 1, which would be 1 cubed plus 3 times 1 squared. This is all over 5 minus 1. So if we figure this all out, 5 cubed is 125, and 125 plus 75, this is going to equal, I'll just carry it down here and erase it after, will be 200 minus 4 over 4, which ends up being 196 divided by 4, which is 49 centimeters per second. So the average velocity would be 49 centimeters per second. Again, note the difference between average velocity and instantaneous velocity. Instantaneous velocity, I take the derivative of the position function. For average velocity, I use the position function in a difference quotient, or basically our simple slope formula, to find the average rate of change. Okay, let's get rid of this so I can do question D. It says, where is the ball when its velocity is 72? So again, we're looking for where the ball is positioned, which is its position. And before we can calculate position, which is our formula right here, we need a time. Well, it's telling me where is the ball when the velocity is 72? Well, my velocity function was 3t squared plus 6t, and that's going to equal 72. So if I set this equal to 0, I'll subtract 72 over. And now solving this, I'm going to factor out a 3, so I get t squared plus 2t minus 24. So this factors into t plus 6 and t minus 4 equals 0. So my two answers for t are negative 6 and 4. Obviously, you cannot have a negative time. So now we're not done the question because we're asked to find where the ball is the position. So the position at 4 is going to equal 4 cubed plus 3 times 4 squared. Okay, so we'll do the math on that. 4 cubed is 64, plus 16 times 3 is going to be 48, and this works out to be 112 centimeters. So again, we had to find time by using the velocity and then use that time back in the position. Find an expression for the acceleration. Well, the acceleration is going to be the derivative of the velocity function. So the derivative of 3t squared plus 6 is going to be 6t plus 6. What is the acceleration when t is 1? So again, to find the acceleration at 1, I just plug 1 into the acceleration function. That's going to be 12 centimeters squared per second. Question G, what is the velocity when the acceleration is 54 centimeters per second squared? Whoops, I got that unit wrong in the previous one here. Sorry, that should be centimeters per second squared. So again, what is the velocity when the acceleration is 54 centimeters per second squared? Again, I need a time. Well, I know my velocity function is 6t plus 6, and I'm going to make that equal 54. That works out to be 48. So t works out to be 8 seconds. So now I'm going to find the velocity at 8 seconds. So I'm plugging that back into the velocity function, which is 3t squared plus 6t. So that's going to be 3 times 8 squared plus 6 times 8. And if we work that out, through 8 squared is 64 times 3 is 192 plus 48 works out to be 240 centimeters per second. Now the last question, we're asked to find the average acceleration between 1 and 5. Again, to find average acceleration, because it's average, it's a difference quotient, it would be the velocity at 5 minus the velocity at 1 over 5 minus 1. Again, this would be in centimeters per second. This would be in seconds, so my unit would be centimeters per second squared. So that's one way to check if you have your formula set up correctly. So now to figure out the velocity at 5, it's going to be 3 times 5 squared plus 6 times 5 minus the velocity at 1 is 3 times 1 squared plus 6 times 1. And this is all over 4. Now I just evaluate this. So this is going to be 75 plus 30 is 105. minus 9 divided by 4. So this works out to be 24 centimeters per second squared. So you have to really be careful with your average velocity and average acceleration. Okay, so one thing to remember, if we're given position, instantaneous velocity, I take the derivative of the position function. Find average velocity, I must be given 2 times, and I use a different quotient with the position function. If I'm looking for acceleration, that's going to be equal to the derivative of the velocity function. Average acceleration, again, I'm going to need 2 times. It's going to be a difference quotient using my velocity function. Okay, in our next example, we have a rock that is thrown upwards from the top of a house, and its height above the ground in meters is given by the following function. So this is really position. Find the initial height of the rock. Well, the initial height of the rock is when time is 0. If I plug 0 into my original function for height, I end up getting 5 meters. Question B, find the velocity after 2 seconds. Well, the velocity is equal to the derivative of the position function, which is going to be negative 10t plus 40. So the velocity at 2 is negative 10 times 2 plus 40, which is going to be 20 meters per second. When does the rock reach a max height? Well, if you think of a rock, it's going to go up, it's going to stop for a second, and then it comes down. So when it stops for that second, the max height is going to be reached when the velocity is equal to 0. So I'm going to take my velocity function, which is negative 10t plus 40. I'm going to set that to 0. Solving for t, I'm going to get time is 4 seconds. So question D says, what's the maximum height of the rock? Well, in this case, I'm going to find the height at 4. So it's going to be negative 5 times 4 squared plus 40 times 4 plus 5. So this works out to be 16 times negative 5 is negative 80 plus 160 plus 5. That's going to be a max height of 85 meters. When does the rock hit the ground? Well, when the rock hits the ground, the height is equal to 0. Okay, so we have to set our height function, which was negative 5t squared plus 40t plus 5 equal to 0. And I have to solve this, so I'm going to use the quadratic formula. So negative 40 plus or minus 40 squared minus 4 times negative 5 times 5 over 2 times negative 5. So if I work out what's under the root sign, I get 40 squared. This ends up being plus 100. And if I square root that, I get 41.23. And this is going to be divided by negative 10. So I end up with 2 times negative 40 minus 41.23 over negative 10, or negative 40 plus 41.23 over negative 10. This will give me a negative time, and I can't have that one. So my only possible answer is going to be negative 40 minus 4.123 divided by, oops, hang on here, negative 40 minus 41.23 divided by negative 10. And this is going to give me a time of 8.123 seconds. So there's going to be the time that it hits the ground. So there's my answer for E. So I'll just put up here, T is 8.123 seconds. Now for question F, with what velocity does it hit the ground? Well, I just take my velocity function, which was negative 10t plus 40. And I'm going to plug in 8.123. So this is negative 10 times 8.123 plus 40, and this works out to be negative 41.123 meters per second. Now, some of you might be wondering, why is it negative? Well, because when the rock hits the ground, it is traveling in a downwards direction, so the negative sign just indicates my direction. All right, in our next example, we're talking about a bee that flies along the x-axis, so its function as a position of time is given by the following. Question A, where is the bee when t is 3? So for part A, we're just asked to find s of 3. So it's going to be 2 times 3 cubed minus 21 times 3 squared plus 60 times 3. And if we work that out, okay, again, I'm going to use technology in this particular case, but to start with, I'm going to graph the function because this is going to come into play a little later on. So our function was 2t cubed. I'm going to use x, so 2x cubed. So 2x to the power of 3 minus 21x squared, so minus 21x squared plus 60x, I believe. Yes. Okay, so I'm going to enter that. I really don't care about the graph right now because I want to use the calculate mode. And I'm going to go to bars, and I'm going to bring in function 1, which is my position function, and I'm going to evaluate it at 3. And if I do that, my position is 45 meters. So again, I'm just trying to introduce technology here a bit. Question B, what is the velocity of the bee when t is 3? So to find the velocity, it's the derivative of the position function, so it's going to be 6t squared minus 42t plus 60. And again, to find the velocity at 3, I'm just going to plug 3 into here. And I can work this out. So this is going to be 3 squared is 9 times 6 is going to equal 54 minus 42 times 3 is negative 72 plus 60. So the velocity at 3 is going to be equal to negative 12. Now, they don't give us any units in the question, so we just leave it as negative 12. Question C says, what is the velocity at 6? So I'm going to plug 6 in, so it's going to be 6 times 6 squared minus 42 times 6 plus 60. So we're going to get 216 minus 42 times 6 plus 60. So the velocity at 6 is equal to 24. So somewhere between 3 and 6, the bee changed direction because the velocity is negative at 3 and it's positive at 6. Question D and E, we're going to do the same. It says find when the bee is flying to the right and when the bee is flying to the left. So what we're going to do is very similar to finding increasing and decreasing. First of all, I'm going to find when is the velocity 0. So this is sections D and E. So I'm going to take my velocity function, which is 6t squared minus 42t plus 60 and set it equal to 0. So if I factor a t out, I get the following, and this factors into t minus 2, t minus 5. So I get 2 times when t is 0 at 2 and 5. So now I'm going to do a velocity number line, and the lowest I can go is 0 because I can't have a negative time here. Okay, and if I do some test points, 1, 3, and 6, we have already tested 3 and 6, but we'll go through it again. If I put a 1, it's negative, negative, it's positive. 3 is positive, negative. 6 is positive, positive. So when the velocity is positive, I know that my bee is traveling right from 0 to 2, union with 5 to infinity, and it's traveling left from 2 to 5. So there's questions D and E. Now for question F, we are asked to find out, show the bee has moved a total of 90 units during the interval 0 to 6. Now, when it talks about moved a total of 90 units, it's talking about distance, not displacement. And since the bee flew to the right for 2 seconds, and then back for 3 seconds, and then back, it will be for 1 second if we stop at 6. We have to set this up in some different ways here. So what I need to do is I need to figure out the position where the distance is traveled from 0 to 2, because that's when it's flying to the right. And I need to take the absolute value of that because that is distance. Distance can't be negative. Then I have to find the distance from 5 to 2, and then finally from 6 to 5. Okay, and I'm going to use my calculator again to save us time because we have these functions stored in our calculator. So first of all, I'm going to find the function at 2, and the function at 2 is 52. Minus, if I put in 0 into my original function, so again, function at 0, it's going to be 0. So that means in the first 2 seconds, it's traveled 52 meters. Then I'm going to go S of 5 minus S of 2. So let's just do that as one calculation. S of 5, so it's going to be my function at 5, which is 25, and S of F of 2 we found to be 52. So 25 subtract 2. This ends up being a negative 27. And if I take the absolute value, it's going to be positive 27. Finally, I need S of 6 minus S of 5. Well, we know S of 5 was 25. And if I go S of 6, it's going to be 36. So this is going to be 36 minus 25, which is going to equal 11. So basically, in the first 2 seconds, he flew a distance of 52 units to the right, and then he flew back 27 units in the next 3 sections, and then 11 to the right. So in total, if you add these up, he flew a total of 90 units. Okay, we'll stop right now, and we'll continue with this in the next video.